Welcome and thank you for attending Mastering the Methylation Panel. My name is Brooke Neve. I am a clinical lab educator here at Vibrant, and I will be your moderator this evening. Vibrant staff and I will respond to questions throughout the presentation, and there will be approximately 15 minutes for live Q&A following the presentation. As a reminder, all attendees are in listen-only mode, so please submit your questions through the virtual Q&A or chat applications. The content of this webinar is for educational and informational purposes only. The information is not intended to treat, cure, or prevent any condition or disease. If you desire medical advice, diagnosis, or treatment, please consult with a medical professional or healthcare provider. And now let me introduce you to today's presenter, Dr. Emaline Brown, who is a clinical lab educator here at Vibrant. Dr. Emaline Brown is a licensed naturopathic doctor and earned her Doctor of Naturopathic Medicine degree from National University of Natural Medicine in Portland, Oregon. After completing her residency at Bastyr University Clinic, she began practicing integrative, urgent, and primary care while eventually serving as Director of Integrative Medicine Services and Naturopathic Residency Supervisor for Healthtopia Clinics in Encinitas, California. Her clinical interests include nutrition therapy, nutrigenomics, integrative urgent care, women's health, dermatology, and preventative care and wellness. Without further ado, I'll turn it over to you, Dr. Brown.
Thank you so much, Brooke, for that introduction. Hello, everybody. Thank you for joining me today for Mastering the Vibrant Methylation Panel webinar. Today, we'll be discussing how the methylation pathway and an individual's unique genetics work in concert to maintain metabolic balance and uncover clinical strategies to address methylation inefficiencies to support overall wellness. We'll begin by discussing the basics of the test before diving into the specifics with a case study at the end to help us illustrate the utility and application of the test. So just bear with me as we get through the markers and the SNPs because at the end, the case is really fun. And it's really where we learn how to apply everything we've just learned, and I think it'll be very useful for you. Okay, so we're going to start by understanding the types of genetic tests available on the market, and so we can understand how ours stands out. So we have commercial and medical genetic testing out there. Generally, these are used for looking at ancestry traits, carrier status, pharmacogenetics. These generally detect predispositions of specific diseases. They're often identifying a mutation in the genome. So, and then we have the functional medicine genetic testing, which is where we fall in today. You can see the purpose of these tests on the right-hand side right here. I'm gonna grab my little laser pointer. And so we have the Vibrant Methylation Panel that falls into the functional medicine genetic testing category, also Cardia X and NutriPro. So these tests are intended to identify actionable SNPs, metabolic weaknesses. They're not disease-based. We can look for nutritional delivery and absorption, biochemical pathways. They are used to help drive lifestyle recommendations, and we're really using them to be proactive and preventive with our patients. As a quick review, let's go over some terminology. Single nucleotide polymorphisms, also known as SNPs, are cutting-edge markers that provide information about a patient's predisposition for dysfunction and subsequent risk of imbalance and/or disease. SNPs are good information, but should be seen as part of a complete picture rather than to be used in isolation to prescribe treatment. It's really not good practice to diagnose or prescribe based solely on SNP genetics alone. You'll also notice the RSID when we go through the report further on. This is the specific location of the gene where the SNP substitution takes place. We have other terminology here that you will see on the report. So as a review for many of you, homozygous wild type. This is a base pair most commonly found in nature, and it's considered normal. Note that this is not necessarily good or bad, but it is the most common found in nature. Then we have heterozygous. This means that there is one base change. It depends on the gene and the RS location, and the heterozygous variant may or may not present a genetic risk based on this. Homozygous variant contains 2 base changes. Usually this presents a genetic risk to the patient. And remember, we're using the terminology variant here because we don't want to refer to our patients as mutants. Nobody wants to be referred to as a mutant. And also note, population studies have taught us that prevalence of SNP type vary between ethnicities and geographical regions. Okay, so what does methylation do? Why should we care about it? Methylation is imperative to many biochemical processes in the body. Everything from hormone, heavy metal, chemical detoxification, nitric oxide production, neurotransmitter metabolism, glutathione production, DNA synthesis, epigenetic modification, which we'll focus on today quite a bit, and more. So what is epigenetics? Well, epigenetics informs the rationale behind the popular phrase, your genes are not your destiny. Epi, meaning upon or above genetics, epigenetics is the concept that influences beyond your genetic code, such as environment, diet, and lifestyle choices, reversibly impact our genetic expression, allowing flexibility in turning on and off genes. For example, nutrients including vitamins, minerals, and amino acids aid in the proper functioning of the methylation pathway. Thus, nutrient deficiencies can affect the pathway epigenetically. Keep in mind, lifestyle factors that have epigenetic impact include exercise, alcohol consumption, the gut microbiome, medication, stress management, etc. Okay, how does methylation work? During methylation, also referred to as one-carbon metabolism, one methyl group is transferred or donated between molecules, as you can see here in this example of DNA methylation. The donor of the methyl group is often SAM, as seen here, S-adenosyl methionine. And this is then converted to S-adenosyl homocysteine, aka SAW. When we are donating that methyl group, it is being turned into SAW, or S-adenosyl homocysteine. And this is the process of transferring or demethylating the methyl group. Methylation is generally associated with switching off or inhibition of a gene, while demethylation is associated with switching on or activation of a gene. We'll review that a little bit going forward. I'll repeat myself because I do think it's a really important point to drive home what methylation generally does in effect to the genes and how it affects us down the line. Okay, so why order the methylation panel? By ordering the methylation panel, we are able to measure functional methylation markers such as B12, folate, and homocysteine. So we can assess via these markers the phenotypic expression of the measured SNP genotypes, which represent only predisposition for enzyme function. And remember, the phenotype is a measurable expression or clinical presentation that we can observe and monitor. This serves to assess the impact of related SNPs, thus enabling the provider to tailor treatment plans to their patient's unique case. The goal is to use the knowledge of these genetic variants to implement precision lifestyle modifications such as diet, supplements, exercise, stress, and sleep management that can improve the functioning of metabolic pathways and prevent, better manage, or reverse chronic disease. Okay, so here we see a list of conditions and signs linked to disruptions in the methylation cycle, and it's quite extensive, as you can see, and there's even more that are not listed here. Okay, and we also have associated SNPs listed that have been associated with each condition or sign, and we have the hyperhomocysteinemia noted if it is related to one of these conditions. This means there is an elevation in homocysteine, which we'll also talk about later. And so if there's a high homocysteine level that might be contributing to this condition, it's listed here. And there are also resources that you'll see at the back of this PowerPoint that you can refer to for your own reference. Okay, so this slide just blew me away, this infographic actually, and so I had to include it. So what we're looking at here is chronic inflammation and its relationship to cancer, because it is so fantastically intricate and intriguing. So when we think about the many influences that impact cancer risk, this figure really drives home the complex relationship that exists amongst chronic inflammation, methylation, enzymes, immune system players, and epigenetics. And so real quick, if we flash this prior, but You can see here increased breast cancer risk has been associated with abnormalities in methylation, particularly the COMT SNP, although those results have been inconsistent in the literature. So as a note there, but in terms of methylation and the effect in terms of the pathophysiology of cancer, we can see this infographic is just, it's so mind-blowing to me. I had to put it in there. Okay. Here we can see just how wide spanning methylation's effect on health is, again, in an illustrated format. So the musculoskeletal system, in cases of fibromyalgia, there may be a methylation impact here. Liver, poor detoxification of toxins and hormones, cardiovascular system, hypertension, hyperhomocysteinemia may have impact on coronary artery disease, for example. Neurologic, psychiatric, mood disorders, Parkinson's disease, Alzheimer's disease, these have been implicated in cases of methylation defects. Gut, inflammatory bowel disease, colorectal cancer, we have seen associations. Okay, so before we dive into more specifics, I do want to mention our Vibrant advantage for the methodology of the methylation panel. So we are measuring a few different things here. For the homocysteine marker, we are using an enzyme assay. This has a high specificity and a quick runtime. For our folate and B12, we are using electrochemiluminescence immunoassay, and this is going to be quicker than ELISA, broad dynamic range, and high sensitivity. So we have benefits there. We're also using real-time PCR for identifying our SNPs. This limits the likelihood of contamination compared to standard PCR and eliminates the need for post-PCR analysis. Okay, so now finally, let's take a look at the test. Okay, so we want to think about the methylation pathways before diving into the SNPs, because that's really going to help us understand the meaningfulness of those SNPs and where they fit into our biochemistry. Okay, so methylation pathways are integral to understanding the function of the measured SNPs and biomarkers. The pathways we feature include not only the methylation cycle, as noted here, but also the folate cycle, as we see here. We also have the BH4, aka tetrahydrobiopterin cycle here, and nitric oxide production here, not to mention creatine, which we need for ATP production, and it's all interlinked. It's pretty incredible. Transsulfuration is noted also over here. We need this for glutathione production. So we can see these are all interconnected. They involve nutrient cofactors and substrates that can be affected by SNPs, which ultimately may logjam, speed up, slow down, or create dysfunction in the system. You can find this handout in your practitioner portal under the educational materials. Feel free to print it out, laminate it, mark it up with dry erase markers, wipe clean and repeat so you can really get comfortable. You know, it is a quite complex pathway, but once you start playing with it, it's a little bit easier. All right. So now we have the key takeaways. So this is really important to understand the pathways as a nice starting place. So let's start to understand the utility. I want to start by looking at SAM. So remember, this is acetinosyl methionine. This can be thought as the body's cash or capital. And so we really need this for all the methylation reactions to occur in the body. We need to pay in SAM cash, if you will, for all those methylation tasks to occur. So once SAM, as we can see here, donates its methyl group, as we see here, it is going to turn into acetinosyl homocysteine, SAW, as we mentioned before, okay? And then after this, after it turns into SAW, it is reversibly converted into homocysteine, as we see right here. And so what's so important about SAW and homocysteine? Well, SAW inhibition of methyltransferases, as we see right here, it ties up the methyl groups. So the methyl group, again, it's right here. It needs to go off and do those many jobs we talked about before. And so SAW inhibition of methyltransferases, it ties up these methyl groups, thus inhibiting global methylation. So it's reasonable to understand why research actually suggests that SAW may be a more sensitive marker of poor methylation status as compared to homocysteine, and also associated risks such as cardiovascular disease, Alzheimer's disease. And so we really, we want to understand, why is it that homocysteine gets such a bad rap? And it may have to do with SAW primarily, but it's easier to measure homocysteine, and we'll see why later. Okay, so luckily, because homocysteine is routinely shuttled out of the cell, we have continuous conversion of SAW to homocysteine. So we see that it is bidirectional, but we want to realize that because it's being shuttled out of the cell, this promotes this forward motion towards homocysteine, so we can recycle it back to methionine right here. This is a backup pathway we'll talk about, okay? Please note, as homocysteine, it's not all bad, because it's going to go this other way, as we'll see in just a moment, into the transsulfuration pathway to support glutathione production. So we need a little bit to go down this other pathway. Okay, and that's right here. So we see the alternate destiny of homocysteine. It's coming from this main methylation pathway, and we are seeing homocysteine coming down here, producing glutathione for detoxification. We also get taurine for energy production in this pathway. And the glutathione production is really why some practitioners shoot for an optimal homocysteine level for their patients, rather than as low as possible, although literature is lacking in terms of human studies and implications of low homocysteine. Okay, so now we want to talk about, how does this all work kind of in a more general sense, to break it down a little bit. Okay, so we'll see there are several factors necessary to drive this pathway and maintain its proper function. For example, for healthy methylation, we need properly functioning enzymes to produce SAM and recycle homocysteine. Here's some food for thought using a simple factory analogy for this biochemical process. In this factory, we want to convert plain blocks to painted blocks, okay? Plain blocks, painted blocks. There's a machine that will do this, and it requires paint to work. Now think of the plain blocks right here as the substrate, the machine as the enzyme, okay, that's right here, and the paint right here as the cofactors for that enzyme to work, and the painted blocks as the active metabolic byproduct. In this case, let's call that byproduct SAM. Okay, what if there's not enough paint? So there's not enough in terms of the cofactors, nutrient cofactors. What if the machine or the enzyme is broken? What happens when there's too few plain blocks or substrate? The answer is always the ability to produce painted blocks or SAM would be compromised. The answer is the same for all three scenarios. We just need to identify what is causing the logjam, and it's generally multifactorial, as is the case with epigenetics. Okay, so now let's look at the report itself. Finally. Okay, so this is a sample of the methylation results summary page. The test includes 12 steps, 3 functional methylation biomarkers, including homocysteine, folate, and B12. Note, we have 3 upregulating SNPs. So generally, a lot of us think of MTHFR as being a SNP that slows down function. Well, these 3, GNMT, BHMT, and MTR, actually upregulate function. All the other SNPs listed here are going to be downregulating. Okay, now we see this is the report. The report will show you the SNP name, the RS number right here, and either a normal or elevated risk with the individual's genotype, represented by red plus signs or blue minus signs, which refer to the variant and wild type allele respectively. So red plus sign, it's going to be the variant representation of that allele, whereas the blue minus sign, it's representative of the wild or the most normal type in nature. That is, again, not good or bad necessarily, but we're looking at the SNPs that are going to confer some sort of clinical impact or risk, and with a red plus sign. Okay, now we have a summary of the functional methylation markers that are necessary to assess overall methylation status. And I want you to remember them as functional methylation markers because they help us assess the functioning of methylation independent of the SNPs. Homocysteine is one serum marker used to assess the phenotypic expression of related SNP genotypes. Elevated homocysteine is associated with overall poor methylation status. So it's a really good marker to just screen for methylation status. And if it's high, you want to think, what do we need to do nutritionally speaking, lifestyle-wise, to help optimize this? Serum folate and B12 are also measured as they are the two most important methyl donors, followed by betaine, aka trimethylglycine, and choline. Okay, so what's all the fuss about homocysteine? Elevated plasma homocysteine is a known risk factor for cardiovascular disease, neurodegenerative disease, mood disorders, and more, as discussed previously. Additionally, the reactions that remove homocysteine are very sensitive to vitamin B status, including B12, B6, and folate, as these vitamins are required for the breakdown of homocysteine. As a result, elevated homocysteine levels can also be indicative of a deficiency in the above-mentioned nutrients. Ultimately, we want to balance methylation and homocysteine by supplying adequate nutrients while keeping in mind other epigenetic influences. Okay, here we have a really nice handy reference guide. So you will have access to these slides again. And so this is really nice just to quickly look up the methylation panels included SNPs with their associated RS number, associated enzyme function, and genotypes. All right, so let's see what kind of SNPs are on this report and what they mean. Here we have the most well-known SNP, MTHFR. I just had to start with MTHFR, right? And I think it will help get our feet wet. A lot of you are already familiar. So, before we dive in, I want you to note that these comments right here are screenshots of the actual methylation report and summarize each SNP's clinical impact. So you can see you don't need to be a geneticist to interpret this test. You'll have all these descriptions populate on your live reports. Okay, for MTHFR, what does it mean? Individuals with homozygous variant MTHFR are more likely to have reduced enzyme activity, leading to impaired folate metabolism. MTHFR SNPs have been linked to various conditions, including migraines, cardiovascular disease and stroke, neural tube defects, depression, Alzheimer's disease, and hyperhomocystinemia. Although, interestingly, a decreased risk of colon cancer. This is a good reminder that SNPs are not black and white. Also note MTHFR 677, this one right here, homozygous variant confers a significant 60 to 70% reduction in enzyme activity, whereas the heterozygous 677 confers a moderate 30 to 40% reduction in enzyme activity. Okay, where does MTHFR fit in the cycle? So MTHFR is an essential step in maintaining a healthy methylation cycle. It's necessary to convert 5,10-MTHF into active folate, noted here. This is going to be 5-MTHFR. Excuse me, 5-MTHF. It's active folate, methylfolate. So we need B12 to do this. And so let's start here. I numbered this so that we can walk through it together. And you want to remember these steps when you're tackling the pathway. So let's start with homocysteine. Number one right here, we want to recycle this back into methionine so it's not going to be vulnerable to converting back into SAW, which we had just talked about. Okay, so start with homocysteine and then work your way from there. And remember that this is the active folate, methylfolate. It's coming into this pathway via this arrow right here. Homocysteine's coming down. We need B12 to join up so we can take homocysteine and turn it back into methionine. Okay, and so this avoids the backing up into SAW, which will inhibit methylation as we talked about before, right? Because if it goes this way, it's tying up methyltransferases and inhibiting the methyl groups. Now that you feel comfortable after reviewing MTHFR a little bit, let's rewind a bit. The SHMT1 polymorphism. This contributes to increased homocysteine by slowing down the conversion of tetrahydrofolate, as we see here, THF, to 5,10-MTHF, which ultimately leads to a deficiency of active folate, again, 5-MTHF. Serine is used as a methyl donor. We see this right here to make methylfolate if it's going this way. Okay, after this point, serine turns into glycine. This is bidirectional, can go either way. So glycine can convert back to serine in support of nucleotide synthesis. So if this pathway is going to the left towards THF, this means the body is deciding to support nucleotide synthesis over methylfolate and recycling of homocysteine. So it's like a seesaw, right? The enzyme must teeter between these two paths depending on metabolic need. Okay, now we have MTR. This is a critical enzyme in the recycling of homocysteine back to methionine using methylfolate and B12 as methyl donors. Individuals with homozygous variant genotype are more likely to have higher MTR activity, and note B12 must be in its reduced form for this to function. Okay, so we want to be mindful that also zinc is a cofactor, and when the SNP is present, activity is upregulated. So it's really important to pay attention to maintaining appropriate B12 levels. MTRR polymorphism will slow down the recycling of oxidized B12 back to its reduced form, which is again essential for recycling homocysteine back to methionine. As you can see, SAM, vitamin B2, and B3 are cofactors for this enzyme. Homozygous variant individuals are more likely to have B12 deficiency. The MAT1A polymorphism slows down the conversion of methionine to SAM. Interestingly, MAT1A SNP has been associated with increased stroke risk independent of homocysteine levels. Individuals with homozygous variant genotype are more likely to have down-regulated enzyme activity and decreased SAM production. Now we have the backup pathway. This one's pretty interesting. BHMT is an enzyme that catalyzes the backup pathway that recycles homocysteine back to methionine, which is very useful when that primary pathway, the folate-dependent remethylation pathway, is compromised, say in the setting of MTHFR SNP. So although BHMT polymorphism is thought to upregulate the recycling of homocysteine to methionine, as we can see here, there is research to suggest that BHMT is associated with loss of function and increased levels of homocysteine due to a mutation of the zinc binding domain, with worsening during times of poor folate-dependent remethylation of homocysteine. And you can see that zinc as a cofactor there. The article also points out in times of elevated homocysteine, liver betaine stores may become depleted, which makes sense, right? Because we're burning through betaine. We need betaine for BHMT to bring this homocysteine back to methionine. And again, because this is an upregulating SNP. Okay, now we have GNMT polymorphism. This upregulates, GNMT upregulates the backup pathway conversion of SAM to SAW. So another backup pathway here. SAM donates a methyl group to glycine, which then becomes sarcosine. See that here. Although this may contribute to increases in homocysteine, particularly again in the setting of an MTHFR SNP, the homozygous variant genotype is thought to have an advantage over the wild type, as GNMT enzyme has been found to regulate genes with antioxidant and detoxification function. So again, we have these little features of these SNPs that we may not be aware of, and they're a little bit more complex than we give them credit for. We want to be mindful that folate supplementation may mitigate the effects of GNMT mutation via support of continuous SAM synthesis. Okay, now we're at COMT. Many people are familiar with this SNP. It does a couple different things, so let's review it. COMT polymorphism slows down the metabolism of catecholamines, such as dopamine, norepinephrine, and epinephrine. Mood and anxiety disorders, including bipolar disorder and anxiety disorder, in addition to eating disorders, migraine, and fibromyalgia, have all been associated with COMT SNPs. These individuals are more vulnerable to stress, but they have pretty good memory and attention on testing. So they prove to actually have pretty good attention to tasks, even though they may have trouble with managing their stress. Magnesium, a cofactor for COMT, as we can see right here, can help increase COMT levels so that catecholamines aren't hanging around for longer and contributing to that anxiety. Also, as COMT is necessary for detoxification of estrogens to less active metabolites, SNPs may lead to oxidative DNA damage, and as such have been associated with an increased risk of hormone-mediated breast cancers, although again, results remain inconclusive. So take note that the research is a bit mixed there. Okay, so now you may wonder about heterozygous individuals when it comes to COMT. Is there a sweet spot for COMT enzyme function? There is research to suggest that the heterozygous genotype, which is associated with intermediate COMT activity and dopamine levels, predicts optimal cognitive performance. Note the inverted U-shaped dose response curve right here from the research article, in which the level of dopamine on the x-axis right here predicts cognitive performance noted on the y-axis here. But pretty interesting in terms of anxiety and, when people are thinking about COMT and driving methylation with methyl donors, that's, I haven't come across research in terms of those heterozygotes, but I thought this study was pretty fascinating, at least in terms of cognitive function and performance. Okay, now we have the NOS and NOS3 polymorphism. This is going to slow down the synthesis of nitric oxide, increasing the risk of cardiovascular disease, such as hypertension and coronary artery disease. Okay, and we can see how this is connecting to the methylation pathway down here. It's all interconnected. So after all that, you might wonder, why doesn't Vibrant measure SAM and SAW? Well, although SAM and SAW are good indicators of methylation status, they are chemically unstable and risk inaccurate results. Therefore, homocysteine, folate, and B12, which are all relatively stable, are measured to assess methylation status on the Vibrant Methylation Panel. Okay, let's move on. We have information on genetic privacy, as this is an important question oftentimes asked by patients, reasonably so. I will skip this slide for now, but you may decide to use it for a future reference after you download the slides. Of course, it's important to have this information to share with patients if need be. You can refer back. Okay, we made it to the case study. Let's learn how to apply all this information for optimal health and wellness. All right, we have Meg. Meg is our patient today. She is a 42-year-old female. She presents with depression, anxiety, fatigue, and headaches, worse over the last year. She's been eating a vegan diet for 2 years. She recently discontinued her birth control pills. She has a family history of stroke in her father at age 50 and breast cancer in her mother. She's taking ibuprofen 3 to 4 times per week for headaches and omeprazole, which is a PPI, as needed for gastroesophageal reflux, about 1 to 2 times per week. All right, so what is her report going to look like? This is the summary page for her. So she has some revealing SNPs that may be contributing to her clinical presentation alongside epigenetic factors, such as lifestyle and diet choices, of course. Keep in mind, her medications are really not doing her any favors in terms of nutrient status and methylation support. To sum it up, she has a variety of genetic predispositions that raise her risk of elevated homocysteine, which is in of itself indicative of impaired methylation status, once again, as we've learned. In addition, she has one homozygous COMT SNP, which may be affecting her mood and detoxification of hormones. Remember that her noted epigenetic influences play a major role in her methylation status and clinical presentation. Note also, you will have access to these slides and you'll see a summary of each SNP when you go through. Okay, so a couple things I want to point out. She has heterozygous genotype for MAT1A. We see that right here. So this may increase homocysteine production via compromised methionine to SAM conversion. You can go back and look at that pathway or print it out from the portal. And this is going to possibly contribute to an increased risk of stroke independent of homocysteine level, as we saw. This is pertinent to her case, right? Because her father has a history of stroke. She has a homozygous genotype SHMT1, which will downregulate the enzyme activity in the folate cycle, leading to decreased methylfolate levels and increased homocysteine. This enzyme requires vitamin B6, which can be depleted with oral birth control and NSAIDs. Other nutrient deficiencies associated with oral contraceptives include folic acid, vitamins B2, B12, vitamin C and E, and the minerals magnesium, selenium, and zinc. A couple other features that I want to point out on this summary report. She has a heterozygous genotype MTHFR right here. This slows down the conversion of oxidized B12 to reduced B12 necessary for remethylation of homocysteine to methionine, compounding an issue of a likely B12 deficiency that her PPI is contributing to most likely, right? The MTHFR SNP may also be implicated in her depression. She has 2 COMT SNPs, predisposing her to poor methylation and therefore poor detoxification of catecholamines such as anxiety-inducing dopamine and adrenaline, and also estrogen and toxins. So she has a family history of breast cancer. This SNP theoretically could further increase her risk of breast cancer, especially in the setting of low vitamin B12 and elevated homocysteine, in addition to possible xenoestrogen exposure and a dysregulated gut microbiome, which are all both too common, right? We see this very, very commonly. Okay, here we can see all of Meg's SNPs highlighted with stars so we can keep track of where they are in the methylation cycle. So this is what I recommend you do. Again, print it out. Per case, it's laminated, right? Because you want it to practice. So we can use a dry erase, mark where somebody's SNPs are so you can understand how it's impacting the biochemistry. So mark it up, play with it. This is a great way to become familiar with the pathways. All right, so now let's see if these SNPs are having a clinical impact via assessment of her functional methylation markers. Okay, right, it might not be surprising that she is experiencing serum B12 and folate that are low, as seen right here, and her homocysteine is moderately elevated. Considering not only her SNP results, but also her medication history of oral contraceptives, a PPI and NSAIDs, and a vegan diet without proper supplementation, it's not too surprising. But these are the epigenetic factors that I'm talking about that, really are going to play a role and, maybe push some of these SNPs to be more so expressed rather than not. Okay, so what are some management considerations and next steps? What do we do about this? Before we talk about diet and supplement options, we want to keep in mind the concept of hyper and hypomethylation. Remember, poor methylation can lead to increase in homocysteine and a slew of health issues downstream. But remember, methylation epigenetically turns off genes, thus silencing beneficial genes in some cases. This is a sweet spot or a U-shaped curve scenario. For example, supplementation with methyl donors such as folic acid and B12 increases the risk of hypermethylation, which has been associated with increased cancer rates and inhibition of tumor suppressor genes. Conversely, hypomethylation is associated with turning on pro-inflammatory, undesirable genes. So how do we attempt to balance this system? Just tell me what to do about it, right? So some just considerations. Start with food first. This is going to be the safest approach. Supplying food-based methyl donors is always the safest approach to support healthy methylation balance. Note vegetarian sources of nutrients to best accommodate MEG are listed here with the animal-based sources in parentheses. So folate, legumes, asparagus, leafy greens, beets, such a great source right there of folate, and particularly betaine, beets again, B12, nutritional yeast, fortified plant-based milk, nori, shiitake, choline. She may or may not, she's vegan, so she's not doing eggs, but we want to think about lentils and soybeans and mushrooms for her. Okay, so once there are adequate methyl donors, as evidenced by optimal folate and B12 levels that you're going to be monitoring to assess her response to therapy, right? Because we're going to repeat those markers. We want to further support her with these DNA methylation adaptogens. And so this may positively influence where her methyl groups are used, particularly for DNA methylation. For example, we want to use DNA methylation adaptogens to our advantage. These are food-based compounds thought to have a modulatory epigenetic effect on DNA methylation that help promote balanced methylation status. The goal is favorable genes such as tumor suppressor genes are turned on because they are not overly methylated or silenced. And unfavorable genes such as pro-inflammatory genes, they are turned off because they are appropriately methylated or silenced. Remember, methylation generally turns off or dials down function. Demethylation generally turns on or dials up function. One study actually showed the flavonoid luteolin, as listed right here, found in Mexican oregano, thyme, and celery, possesses demethylation properties thought to contribute to its anti-cancer effect. How cool is that? All right. So vegan diet, we know, is low in choline. This is necessary to support cell membranes, cognitive function, mood, and betaine synthesis. You may also consider a beet or betaine supplement in addition. And so now we've moved on to the supplements, if you're still really not hitting the mark with these micronutrients. And we also want to consider a high quality protein powder to supply sufficient methionine, which also supports taurine synthesis, assess nutrient status of other minerals such as zinc and magnesium and other B vitamins not included on the methylation panel, with micronutrient testing, which we do offer with our micronutrient 3.0 test, and supplement those as needed based on testing, not guessing, and monitoring as you go. Supplementation to support methylation with active B vitamins has become really second nature to many of us, but there's good reason to be a bit more discerning due to the risk of harm with hypermethylation, as we just saw. So consider supplementing only as needed, okay? For folate, consider methylfolate supplementation rather than folic acid. Folic acid is convenient because it is shelf stable, but it's also synthetic and poorly converted to active folate in many. Research has shown unmetabolized folic acid paired with low B12 status has been associated with reduced cognitive performance. And then we have for B12 this handy reference guide, which outlines clinically relevant pros and cons of each form. Note that the methylcobalamin and the adenosylcobalamin right here are both active forms of B12. So they may be preferable to the other two, but the cyanocobalamin is really, it's the only synthetic form listed here. All right. So once you have a good idea of your patient's SNPs and their methylation status based on their functional methylation markers, we want to consider ordering additional tests to round out the picture a little bit more. So total tox, neurotransmitters, gut zoomer, NutriPro, and our urinary hormone tests are really fantastic companion tests. These tests will help us assess toxic burden, neurotransmitter levels, the gut microbiome, and digestion, both of which can impact nutrient absorption and nutrient status. Micronutrient status with related nutrigenetic SNPs, which you get with the NutriPro here. And so that's basically the micronutrient 3.0 with nutrigenetic relevant SNPs included. And then hormone metabolism, of course, you can evaluate with the urinary hormone metabolites test. All of these factors may impact our epigenetics and be impacted by our genetic makeup, as we have just learned. One example is the fact that the gut microbiome has been found to impact folate status. Bifidobacteria appear to be folate producers, while lactobacilli folate consumers. Found that fascinating. So again, there's so much you can get from a comprehensive stool analysis. So don't forget about the gut zoomer. It's got a lot of great data on there. Okay, and with that, I will conclude our presentation. Thank you so much for attending. I think we have some time for questions.
Thank you, Dr. Brown, for such an informative and meaningful presentation.
Sure.
We will now begin the Q&A, and we have a couple of private questions come through. So the first one was, how do you suggest providers monitor methylation status over time?
So you want to think about these functional methylation markers, right? So the genetics don't change. And so our homocysteine, B12, our folate, these are markers we want to look at going over, in the future, and to see how are they responding to treatment, particularly the homocysteine. If you're bringing it down within range, that's a good sign that the methylation status has improved. And remember, the homocysteine is one of the best indicators of overall methylation status. So high homocysteine, poor methylation status. You could also consider other markers too, like RBC folate and MMA. for a little bit more information on that.
We have a question about repeat testing. When should I repeat this test?
Yep, great question. As I just said, this is our genetics on the methylation panel. So our genetics don't change. So that's kind of the good thing. I think everybody at least once we want to be mindful that these tests are out there. And so there are similar tests where it's looking at genetics, but with those particular SNPs, they're not going to change. So you run the methylation panel once, and then those markers that I just talked about, folate, B12, and homocysteine, you'll want to think about running those. Maybe you can start out maybe 3 to 6 months. Once you get into the optimal range or your target level, maybe consider running annually.
We have a new provider to methylation. They want to know if you have any resources or tips for providers starting out.
Yeah, great question. I think that, there's a lot of information here. It can be a little overwhelming. And I would say order the test. We're clinical educators. We're here to walk you through the interpretation. So order the test. Seems obvious, but the more you see, the more practice you'll get and the more understanding you will obtain. So again, order the test, print out the pathway, mark it up so you can play with it. For each individual case, when you're ordering this test, you'll you'll understand patterns that are emerging, and again, that biochemistry using that nice visual guide in terms of the methylation pathway. A few books you could also consider: A Younger You by Dr. Kara Fitzgerald, Dirty Genes by Dr. Ben Lynch, Nutrient Power by Dr. William Walsh. These are all really helpful books also to learn more about epigenetics and methylation.
I love the tip too, about the laminator. I need to get myself a laminator now so I can mark up the pathways.
Absolutely, and save yourself some paper that way too.
Yeah. Okay, a sample collection question. What tubes are needed for collection?
So this is really straightforward collection for methylation panel. It's just one serum SST tube and one lavender EDTA.
Okay. Here's a question. Does Vibrant have any other genetic tests, or do you offer additional SNPs to add on to this test?
Great question. So we don't have add-ons for the methylation panel, not that I'm aware of, but we do have additional genetic tests. And so the Cardia X is a genetic test that is identifying SNPs related to cardiovascular disease risk. And then the NutriPro, as I mentioned before, it has everything on the micronutrient 3.0 plus nutrigenetically relevant SNPs. So if there's an issue in terms of absorption of a nutrient, genetically speaking, you'll see that SNP on that report. And so you might be struggling to get somebody's nutrient status at a certain level, or despite your best efforts, supplement or dietary modification wise, and there may be a SNP that might be impacting those levels and the absorption of them or the transportation of them into the cell. So we do offer those, and they're great tests. Also, you want to consider the epigenetics that could be influencing those results as well.
And what are some lifestyle tips to support healthy methylation?
Oh, yeah, sure. So, I'm harping on epigenetics. So great question. We talked about diet and supplementation, but, I really can't stress enough supporting the gut microbiome. Our gut zoomer has inflammation and digestion markers on there. So this is really going to impact our nutrient status, and particularly folate again. So if we're not absorbing these nutrients, we're really not going to be supporting our methylation pathway, right? So we're thinking about, did somebody have these nutrients? But the first step is really proper absorption at the GI tract. So I would, start with gut health. That's such a common recommendation. And then be mindful of certain medications. That's another thing. Things like, again, birth control pills, proton pump inhibitors, antibiotics, cholestyramine, these may interfere with methylation. So being mindful to get a really good history, a double check with patients, because sometimes they're not reporting everything that they may be taking, particularly OCPs. I find that people forget to report that. And let's see what else. Environmental toxins. I mentioned the total tox test. You want to be mindful of the toxic exposure that we all really have to contend with in our modern world. Chronic stress, chronic infections, elevated estrogens, high histamine diet. All of these things actually can impact our methylation status and impact it negatively. So all of those you want to really be mindful of.
Excellent.
What else? Anything else? Let's see. I can take a look too. I think we covered it. Is there anything else you see, Brooke?
Nope, that's it. And thank you for your questions. If we didn't get to any, or you have one that pops up later, you can always email your question to us at clinical@vibrant-america.com. And thank you everyone for your engagement and your business. Vibrant appreciates your support and the work that you're doing to advance the functional medicine, disease prevention, and wellness model. Immediately following this webinar, you will receive a short 5-question survey. Please complete the survey so we can gain insights into how well we're meeting your needs, or how well, or how we may improve the clinical lab education program, products, and services that we offer to you. Thanks again, Dr. Brown.
Thank you, Brooke.